Welcome, everyone. Ready to dive into some serious brain-tickling stuff today. We're going deep on the uncertainty principle, but not in that usual physics-y way. No, we're going to tailor this specifically for you, a philosopher out there.
Oh, it's amazing how this principle, right, it goes way past just physics, really gets into like, what is reality even? Knowledge and just what can we even know? Huge philosophical questions, really.
It's true.
Yeah.
And lucky for us, we've got a top-notch guide, the Stanford Encyclopedia of Philosophy's entry on, well, the uncertainty principle, obviously. That's some serious philosophy of science stuff right there, really in-depth. So yeah, get ready because things are about to get seriously mind-bending. Now, I got to say, this principle, it's not just about, oh, we're a bit unsure about things. It's a precise statement, but a very specific kind of unknowability in the quantum world.
Exactly. To really get what it means, we got to first wrap our heads around how quantum mechanics totally shook up our understanding of the physical world. Like in classical physics, we're all, yeah, we can totally know a particle's position and its momentum at the same time. No problem.
It's like a perfectly predictable world.
Yeah.
Right. If we knew how everything started, we could theoretically predict everything. But then, boom, quantum mechanics crashes the party, and suddenly that neat and tidy world is out the window. So, how does this uncertainty principle fit into this new kind of crazy picture?
Well, the uncertainty principle basically says, hold on, there's a limit to how well you can know both the position and the momentum of a particle at the same time. It's like the more you nail down one, the fuzzier the other gets. And get this, it's not because our instruments are messing up. It's baked right into the nature of quantum systems, man.
So it's not like the electrons being sneaky or anything. It's like the uncertainty is just a part of reality down there at the quantum level.
You got it. No, we got to give credit where credit's due. Werner Heisenberg, he's the one who first put this into words back in 1927. But he wasn't just about equations. He wanted to make quantum mechanics more down to earth, connect it to what we can actually see happening.
Right, right. There's that word, Anschaulichkeit. It's like wanting physics to be visualizable, understandable. He was bridging the gap between all the crazy math of quantum mechanics and what actually happens in experiments. Right?
Exactly. His whole thing was, if you can't describe an experiment to measure something, then like what's even the point of that concept? You got to be able to measure it. And that's where his famous microscope thought experiment comes in. Super elegant way to show this principle.
Yeah, okay, let's break down this thought experiment. It's about trying to see where an electron is using a microscope. Right?
Yep. So imagine shining a light on an electron. You want to see where it is. But to get more precise, you got to use a light with a shorter wavelength. The catch is, shorter wavelength means more energy in that light.
So it's like you're trying to find this tiny speck of dust in a dark room. You need a brighter flashlight, but if it's too bright, poof, you might blow the dust away.
Perfect analogy. That high-energy light, when it hits the electron, it gives it a momentum kick, making its momentum more uncertain. So trying to nail down the position messes up the momentum, you see. And the same thing happens the other way around, too.
It's like there's this cosmic balancing act between knowing the position and the momentum. Now, this is where things get super philosophical. What does this uncertainty really mean? Are we just limited in what we can know? Or does it say something deeper about reality itself?
That's where these different interpretations come in. We've got the epistemological interpretation, which says, hey, maybe the uncertainty principle is just about the limits of what we can know.
So, like, the electron might actually have a specific position and momentum, but we just can't get both pieces of information at once. Our knowledge is limited, but reality might not be fuzzy.
Exactly. It's like peeking into a box through a tiny hole. You only see a part, but the whole thing inside isn't necessarily blurry. Then there's the conceptual interpretation, which gets a bit more radical.
Okay, this one, if I get it right, it asks if our normal ideas of position and momentum even make sense in the quantum world. It's like trying to describe the taste of chocolate using only colors. The words just don't cut it.
You got it. And lastly, we got the heavy hitter, the ontological interpretation. This one goes straight to the heart of things, saying quantum systems just don't have a definite position and momentum at the same time, period. The uncertainty is not just in our heads, it's built into reality itself.
Whoa, so the electron isn't hiding anything. It's more like those properties don't exist until we measure them, right? It's like saying a coin doesn't have heads or tails until it lands.
Perfect analogy. Heisenberg himself, he kind of danced around these different ideas. He was big on like measurement equals meaning and measurement equals creation.
So measurement equals meaning means you can only talk about something if you can measure it. And measurement equals creation means the act of measuring kind of makes that property real.
You got it. And that's where the deep philosophical debate kicks in. Is the uncertainty principle just how we're forced to interact with reality, or is that truly how reality is? Does uncertainty belong to the system itself, or do we somehow cause it by looking at it?
That's a huge question, taking us way past physics into, like, metaphysics and epistemology. But before we jump into that rabbit hole, I gotta ask, does this whole uncertainty principle thing even deserve to be called a principle?
Oh, you bring up a good point. Even Karl Popper, big shot philosopher of science, he wasn't on board with calling it a principle. He was like, if you can derive it from a theory, it can't be a fundamental principle.
So in his view, it was a result of the theory, not a starting point. But Heisenberg himself seemed pretty keen on the idea that it was based on what we see in experiments. How do we square those two ideas?
To make sense of that, we got to look at how Einstein separated constructive theories from principal theories. Constructive ones, they start with basic stuff and build a model. Principal theories, they start with what we actually observe and see what pops out.
So like classical mechanics, it's all about forces and stuff. That's constructive. But thermodynamics, with its laws of entropy and energy, that's more about observing patterns, right?
Exactly. So maybe the uncertainty principle, it's actually an empirical principle, just like those laws of thermodynamics. After all, Heisenberg himself said it comes from pure fact of experience.
Interesting. It's like we could view it as a basic rule about the world we can observe, not just some math thing from quantum mechanics.
That's where philosophy really steps in and helps us unpack these ideas. It lets us move past the equations and really grapple with these huge questions about reality and what we can know. So if we're going to call this thing a principle, got to make sure it actually holds up in the real world, right? Like, does it pass the experimental test?
Yeah, that makes sense. There have been tons of experiments trying to test this principle. What's the verdict?
Well, Heisenberg's early ideas were thought experiments, just thinking things through. But later on, experiments backed him up pretty solidly. But of course, science is never about proving anything absolutely right.
Right, experiments can only show if a theory seems to be working or if it's totally busted. So we're saying the uncertainty principle matches what we see, but we can't be like, boom, proven.
You got it. And that leads us to another layer of this whole thing that philosophers love, measurement and disturbance. Heisenberg, he thought that when you measure one thing, like position, you mess up the other, like momentum.
Yeah. It's like trying to check your tire pressure. You stick a gauge in there, you get a reading, but oops, now you've let some air out.
Such a good analogy. But here's the thing. This whole measurement disturbance idea wasn't in Canard's inequality, which uses standard deviations to talk about uncertainty.
So Canard's inequality is more about the spread of possibilities, not about one specific measurement messing things up. So how do we connect Heisenberg's idea to the math?
Well, that's where all this modern debate about error disturbance comes in. People are trying to put Heisenberg's idea into more precise math terms. Masanao Ozawa, he took a good stab at it. He imagined a quantum system like our electron interacting with a measuring device.
So he's factoring in the act of measuring itself, saying it's not just watching, it's an interaction that changes the system.
Exactly. Ozawa came up with these quantities for both the error in measuring something and the disturbance you cause to the other thing. Then he came up with an inequality, but it didn't have a lower limit.
Wait, no lower limit? Doesn't that mean we could theoretically measure both things perfectly, which would totally contradict the uncertainty principle?
That's what his results seem to say. So he concluded that Heisenberg's error disturbance thing doesn't always apply. You can imagine this stirred up a whole lot of discussion.
Of course. It's like saying, nah, we can actually know both where an electron is and how fast it's going. That goes against everything the uncertainty principle is about. So what did other physicists say about that?
Right. Well, other folks like Paul Bush, Pekka Lotti, and Reinhard Werner, they had a different approach. They used something called positive operator valued measures, or POVMs for short, to describe trying to measure position and momentum at the same time.
Simultaneous measurements, even though we know we can't be perfectly accurate with both. It's like trying to taste and smell a strawberry with the same tool, right?
Yeah, I like that. Their approach, we call it the BLW approach, gets that every real-world measurement is a bit fuzzy. They use this special math tool to compare the results of their joint measurement to what you'd get if you could measure each thing perfectly separately.
So they're basically measuring how much the joint measurement is off from the ideal case, showing how the act of measuring adds uncertainty. What do they find?
Well, they came up with a new uncertainty relation, and this one did have a lower limit. They said the inaccuracy in measuring position times the disturbance to momentum, it has to be bigger than some constant value, kind of supported Heisenberg's original idea.
So the BLW approach backs up Heisenberg,
Yeah.
even though they're using fancier math than those standard deviations in Kennard's inequality.
That's what they're saying. But even this approach has its quirks. Some folks criticize it, saying, yeah, the math works out, but it might not apply neatly to real-world experiments. Their derivation used a bunch of possible quantum states, basically the worst-case scenario.
So it sets a limit in general, but doesn't say what'll happen in one specific experiment with a specific state. It's like knowing the speed limit, but not how fast the cars are actually going.
Right on. So the BLW relation, it's theoretical, but doesn't totally capture the details of a particular experiment.
This really shows how theory and experiments dance with each other, right?
Yeah.
Seems like this whole error disturbance discussion and what it means for measuring things in quantum mechanics is still a lively debate.
Absolutely. And things get even more interesting when we start thinking about the philosophical implications of all this.
All right, let's wade into those philosophical waters. What are the big questions that these error disturbance relations raise for someone thinking about the nature of reality and knowledge?
One huge question is, do these relations mean that quantum properties are fundamentally uncertain, not just unknown? Like, it's not just us missing information, but that the properties themselves are fuzzy until we measure them.
So measuring isn't just revealing what's already there, it's actually shaping reality in some way. Heavy stuff.
You got it. If we take these error disturbance relations seriously, it seems like measuring something fundamentally changes it.
Wow, that's a massive change in perspective. It challenges the whole idea that we, as scientists, are separate from the stuff we're studying.
Definitely. If our measurements are shaking reality, then we're not just watching, we're part of the whole quantum dance.
That's wild. Like saying that looking at a star changes the star itself.
And it gets even crazier when we think about cause and effect.
Now you've got me hooked. How does the uncertainty principle, especially this error disturbance stuff, mess with our usual ideas of cause and effect?
Well, if measuring something changes it, then it's hard to say what caused what. Did the measurement cause the change, or was it something else?
Because the act of observing is mixed up with the system changing over time. So it blurs the line between cause and effect, something that never happened in classical physics.
Exactly. It suggests that cause and effect, the way we usually think about them, might not work the same way in the quantum world.
So the uncertainty principle isn't just about not knowing things, but also maybe about the limits of causality itself. That's a truly mind-blowing idea for a philosopher to ponder.
It is. It makes us rethink time, the role of the observer, and what objective reality even means.
We've really stumbled into a deep philosophical rabbit hole here. Let's take a breather and look at the big picture. What are the key takeaways for you from all of this? Okay, so we've talked about how the uncertainty principle really messes with our classical physics view of the world, especially the idea that measuring something inevitably disturbs it. It challenges the way we think about observer and observed, even cause and effect. But you mentioned some alternative ways to think about uncertainty beyond using standard deviations, right? What are some of those, and what new insights do they bring?
Well, one approach that really appeals to those seeking a deeper understanding is the use of bulk widths to quantify uncertainty. Instead of focusing on the average spread of a distribution like standard deviations do, bulk widths look at a specific interval that contains a large chunk of the total probability.
So it's like saying, hey, 90% of the probability falls within this range, so let's use that as our measure of uncertainty. Seems more intuitive, especially for distributions with weird outliers.
Exactly. And the cool thing is we can get uncertainty relations using bulk widths that are different from, but also complement, the Heisenberg-Kennard relation. They give us a fresh perspective on the same fundamental principle.
It's like approaching the same philosophical problem from different sides, using different tools to shed light on its various aspects. It shows how rich and complex the uncertainty principle is, how it keeps sparking debate and exploration.
Exactly. And then there's another really fascinating approach that uses the concept of entropy to quantify uncertainty. You might know entropy from thermodynamics, where it often relates to disorder or randomness.
Right, the idea that things tend to get more disordered over time. But how does entropy connect to uncertainty in quantum mechanics?
Well, in information theory, entropy is a measure of information content. The basic idea is the more uncertain we are about something, the more information we gain when we measure it.
So a system that's very ordered with low entropy wouldn't have much uncertainty because we already know a lot about it. But a disordered system with high entropy would have lots of uncertainty because it could be in many different states.
Exactly. And we can use this idea in quantum mechanics with something called Shannon entropy, which measures the information content of a probability distribution.
So instead of standard deviations to represent the spread of possibilities, we're using entropy to measure how much information the distribution holds. How does this give us a new way to think about the uncertainty principle?
The really neat thing is, we can derive uncertainty relations using entropy that are actually stronger than the Heisenberg-Kennard relation.
Stronger meaning they put tighter limits on how much uncertainty we can have about position and momentum together. So we're getting an even more precise understanding of the fundamental limits in quantum mechanics.
Precisely. And these entropic uncertainty relations aren't just some mathematical trick. They're giving us new insights in areas like quantum information theory and quantum cryptography.
So the uncertainty principle, despite its name, is actually opening up new avenues of research in these cutting-edge fields, shows the power of these fundamental principles to drive innovation and discovery.
Absolutely. It's a great example of how an abstract concept can have huge implications for both how we understand the universe and how we develop new technology.
As we wrap up our deep dive, I'm amazed by how the uncertainty principle has shattered our old classical physics intuitions. It's made us rethink what reality is, what it means to observe something, and even what knowledge itself is.
It's a reminder that the universe is far stranger and more amazing than we could ever have imagined, and that we're always learning and discovering new things.
For a philosopher, the uncertainty principle is full of questions and challenges. It makes us grapple with the limits of what we can know, the nature of measurement and observation, and the very essence of existence itself.
It's a concept that keeps sparking debate and new ways of thinking about the world. As we've seen, exploring its different interpretations and formulations can give us profound insights into the very nature of reality.
Well said. Thank you for joining us on this deep dive into the uncertainty principle. We hope you've come away with a deeper understanding of this mind-blowing concept and its power to challenge and inspire us.
And maybe even a little bit of that wonderful uncertainty that keeps us questioning, exploring, and seeking deeper understanding.